Okay, so we're going to do a quick demonstration of how to set up an assembly language program on MPLAB X IDE to make a series of LEDs flash from the left to the right in a chase pattern, so to speak. If you don't have MPLABx, you can download it from microchip.com/MPLABx. It will come with the ASM assembly language compiler. If you want to do this in C, then you'll have to find another demonstration video and download the high-tech C compiler from Microchip as well. This particular instruction video will show you how to set up from 18F 45K20. You may have to change some lines of code if you're using a different series PIC chip, use different counters, you're going to have different registers and all of that, but all of that is available in your data sheet that you can download in PDF format from microchip.com. So first thing you'll do is open MPLAB, and when you do that, you'll be at the start page. From the start page, you have several different options how you want to create a new project. You can scroll down and click it there. You can do it from the file menu, or you can just click the folder, which is how I usually do it. Microchip embedded is what you're going to select. Standalone project, next. Then you'll find your PIC. You can choose all families, or you can narrow it down by your family. Mine would be the 18 advanced 8-bit MCUs, but I'm just going to do recently used because that's the PIC that I'm using. Click next. Then you'll select which hardware tool you have. I have the PIC18F. And then you select your compiler. I'm using the mpasm. I call it mpasm. And then next. Then you'll create a new name, so we'll say new project. And then click finish. Then it'll create the project here. Once you've opened up your new project, the first thing you want to do is add your linker file. So go to linker files, right click, and add an existing item. To get to this linker subfolder, you'll have to navigate to your main disk and program files and Microchip. In Microchip, you have to go through MPLABx, and then for this assembly linker file, you need to go to mpasmx or mpasmx. In there, you have several different things here. Here's all your include files, and then you have some templates. If you want to start your main ASM file, you can use either a code template or an object template, and if you want, you can read the difference between them in the README. But we're not going into that in this demonstration. So right now we're going to add our linker file, which is in the LKR folder, and the file we select is going to be the 18F 45K20_G.linker, which if you scrolled over this way, you would eventually find 18F 18F 45. See, this is why I don't do that. 18F 45K20. And select, and then you'll see it adds it underneath your linker files. Then you want to right click, source, new, empty file, and here you'll call it whatever. We name this project new project, and make sure you put .asm as your extension. Otherwise it'll just be an empty text kind of document, and the compiler won't really see it. It won't know what it's doing. So you need to have it as a .asm extension. So once you've added your new file, it'll show up here, and from here you can put your config commands, or enter your text with a semicolon, and then text here, whatever you want to put, and then all your commands, and it sees it. You can see it highlights, you know, it changes the different colors. You know, made config violet, made just the plain text, which is your notes, green. You know, if you did an org command, you know, to change it blue. So, but I'm not going to do this because I've already written it out. So I'm just going to discard this, and I'm going to close this project and just show you the one that I've already done, which is the timer LED chase. Now, as you can see, I start off with a header with my title, my date, my name, and a description. This program causes the LEDs on port D to chase each other back and forth. Then I go on to the configuration setting. Configuration settings, I want to start with my list command, which tells it which PIC I'm going to use. PIC18F 45K20. And then my hashtag include will tell it to include this file, which basically tells the PIC, well, it tells the compiler the memory organization and different aspects for creating the hex file for this specific PIC family, or this specific PIC in general. That way I don't have to define every, you know, every port, every register, you know, all of that stuff. So once I've done that, I'll go into my configuration, and first thing I do is I turn off the watchdog timer. For my PIC, the command is watchdog timer enable. Some PICs it's just WDT. You really have to check your data sheet to find out what the exact commands are for your PIC. Next, I'm going to disable the port B analog inputs, and by disabling it, I'm going to make it to where only digital inputs can be used. I'm not really using any inputs on port B in this demonstration, but I just kind of have been doing this because I haven't used analog ports yet. I'll be doing that in my next task, I guess, which is to use the pulse width modulation. And when I get that going, I guess I'll put a video up for that as well. And then I'm going to turn the master clear reset off. Again, it's not necessary, but it'll disable the master clear, you know, and it makes it so that you can use that as another input. And then I'll turn off the low voltage programming, and I'll turn off the debug because I won't need either of those for such a project. I'm not really sure what the LVP is for, possibly when you're doing in-circuit serial programming, but I won't be using it. And then the debug, this is such a simple program, I won't need it. And next is to configure the oscillator. This can be a little confusing. Make sure you look at your data sheet. For mine, I wanted to select the internal oscillator, and I wanted to use divide by 4 frequency output on port A, bit 6. So the specific command is config fosc, and then basically I say, okay, fosc equals internal, so that tells it to use the internal oscillator block. And then I'm telling it that I only want the I/O on pin 7. That way it automatically gives me divide by 4 F out on RA6. I could put internal I/O 7/6, and then I would make both pins 7 and 6 available for input output, but I don't really need it, and I kind of like seeing the output on pin RA6. That way I know for sure that it's set up properly. And for you new fellas, the input output pins RA7 is if you're going to use an RC oscillator, you would usually set that up on pin 7 between resistor to power and a capacitor to ground, and both of them going to pin RA7. The next section I'm going to set up is my definitions. Now, I'd like to note here that when I wrote this code, I didn't write it linearly like this. I actually wrote I think the next thing I did was my initial settings. And when you write code, you don't always think linearly like this, and you have to go back and rearrange it to make it look neat later on. So that's pretty much how this works. But in my definitions section, I'm going to define this register value, this memory address, which is a hexadecimal 50, which is just a general purpose register, and I'm going to call it skip to simplify things. And then I'm going to set the timer 0 count variable, and that's going to go to register address hex 20. And that's just, I'm going to put a value into that register, and then every instruction clock cycle take 1 from that value until that value gets to 0. And that's gonna set up the timing between, you know, when the LEDs are gonna shift. So I used the cblock command. I could have used the same command here. I could have just said timer 0 count equals 0 by 050 or whatever, 020. But I'm just kind of showing you a couple different ways you can do it. This is considered a variable, and I'm not 100% on them yet, but I believe what you can do is you can define multiple things here, like cblock 0 by 020. I could do timer 0 count, I believe, comma, and then put another label, and then that would assign something to 0 to 1 hex, and so on until I finally do my end C command. Next, I'm going to set it up so that the code will begin at memory address 0 hexadecimal, and that's going to go to my initialize section down here, my initial settings. And then for my particular PIC, from the data sheet, it's noted that hex address 08 is the high priority interrupt, and so I've told it that at 08 I want it to go to the interrupt HP, which is high priority interrupt routine. So after the definitions, we get into the main guts of the program. As you'll see down here in the main section, there really isn't any commands, so everything happens during the interrupt, really. Okay, so stick with me because I know this might get confusing. So the first thing that happens when that interrupt is issued is it's going to come to the int HP label. And here I'm going to do a bit test to see if the timer 0 interrupt flag has been set. If it has been set, then I'm going to go to the next label, which I've created as the interrupt timer 0 interrupt flag. Okay, if it's still clear, if it hasn't been set, then I'm going to return from the instruction. And returning from the instruction is basically going to put me right back here in the main program. Now I'll come back up. So my flag has been set, and now I go to the int timer 0 if label. First thing I'm going to do is start decreasing the value of the overflow counter. And if it's not 0, it's going to return from the instruction. It'll read this command, the go-to command, and it'll go down here where it basically clears the interrupt flag and sends it back up here. Well, it sends it back to the main, and then after the main, it comes back up here and it checks that flag again, and then it'll come here because the flag will be set, and it'll say, okay, well, I'm still not 0, and it'll keep doing that until it reaches 0. When it reaches 0, I'll go ahead and reload the register with the starting count. And by doing that, what I'm going to do is, or to do that I should say, what I'm going to do is move this value into the working register, the move LW command, and that's an arbitrary value for whatever period you want it to take between the bit transition, really. So I've chosen 3, it's a good value, and for the speed that I'm using. And then I'm going to go to the move from the W or working register to this register, whatever register I call, which I'm going to use the timer 0 count. And remember, we defined that earlier up here at hex 20, so that's where I'm loading this hex 3 value. So basically 3 instruction cycles, kind of, you'll see later, the 3 counts, and then we'll say, okay, let's go ahead and rotate the bit. So after I've reloaded the counter, the overflow counter, and moved it, I'll come here and I'll do another bit test. This time I'm going to test to see if bit 1 in the skip register that we defined in the beginning has been set. If it's set, then I'll skip the rotate left command and I'll go through a series of commands to rotate to the right. But when we initialize the program, it won't be set, and so we'll start rotating to the left right here. After we rotate to the left, we'll come here and we'll say, okay, we'll do another bit test to see if the status flag, the carry flag in the status register has been set. If that's been set, then we'll go here to skip, and if we, where we set the skip bit, once that bit is set, then it'll test the skip bit. If it's set, it'll start rotating to the right. But initially it won't do that because it'll say, oh well, my carry flag is still clear, and since my carry flag is clear, then I'm going to skip the next command and I'll go here, and it'll say, well, of course the skip register doesn't have the bit set yet because we just skipped that command. So I'll go ahead and skip the rotate right command, and then I'll check RD0. Now here I'm going to test to see if it's clear or if it's set. And if it's clear, I'm going to skip the next command, go back to the main, come back up here, and then start going, continue going to the left. Now let's look at what happens when we get all the way to the left and the carry flag gets set. So as the bits are rotating in the right, or I'm sorry, as the bits are rotating to the left, eventually you'll get to RD7, and then once we do another rotate to the left, the carry flag will be set inside of the status register. So when that happens, we'll come down here and we'll say, oh well, the status flag has been set. The carry flag in the status register has been set. So now we need to go to the next command and we need to set the bit in the skip register. So once we've done that, we'll check the skip register bit again. And if it's set, which it should be because we just set it, previous command, then we're going to start rotating back to the right from RD7 towards RD0. So once we've done that, we'll do another test to see if RD0 has been set or if it's still clear. If it's still clear, we skip this command here, go back to the top, and everything is still set up so that we're going to continue rotating to the right. When we finally get to RD0, it's going to say, okay, RD0 is a 1 now. It's been set, so we need to clear the skip register, so when we come back around again, now we're going to start rotating to the left. I hope I didn't confuse you there. I know it's a little convoluted when you're starting out fresh. It took me a little bit to write this program because I'm new to this as well. So now we have one more label within our interrupt routine, and that is the int timer 0 if return. And what that does is up here, when we started decrementing the counter to see if we'd reached 0 yet, if we hadn't reached 0, we said, well, come here and clear the interrupt flag. That way You know, we can keep doing this until we get to 0. So that's just another way to keep decreasing the value of the overflow counter until we got to 0. And then the next section we're going to look at is the initial settings, which is basically setting up a lot of the values to make this work. Okay, so in the initial settings, the first thing I decided to set up was my oscillator. Now, yes, it's true that we enabled it up here. We said that this is what we want to use as the internal oscillator. But we didn't tell it how we want to use it, what frequency, what we're going to do. So basically, I have 3 bits that allow me to determine the desired frequency that I'm going to use. And I've decided to use the full 16 megahertz in this example. And so in the oscillator control register, which is OSCON, I have 3 bits that I can use to determine the frequency. And those are the IRCF 0 through 2 bits, which is internal oscillator. You know, so I have to set all of those high if I want to use 16 megahertz. If I wanted to use a different frequency, you know, some of these would be bit clears. But another way I could do this is I could move a value to the working register and then move that to the port, or the register. I'm sorry, I always call them ports. I move it to the F register, which would be OSCON in this case. So I would do a move LW, and I could enter a binary number or a hex number or a decimal number, but I have to know what it converts to. So I would put that value in and then do a move WF into the OSCON register. For me, it was just easier to just set the individual bits, and so that's how I chose to do it. Next, we're going to disable all the A to D converters and the comparators. Well, really there's only one A to D converter, and I have 3 comparator modules on this chip. So again, by looking at the data sheet, and for the A to D control register 1, I've determined that I need to set a hex value of F to disable it. And then to disable the control registers for the comparators, I had to move this value, hex 7, into those registers. Next, what I'm going to do is clear the tri-state A, or tris A, I call it tri-state, register. And what that does is sets all my bits on port A to output. And then I'm going to do the same thing for port D, because port D is where I'm going to make my LEDs roll from the left to the right and the right to the left. Then I can do that just by doing a clear F, or I could do it individually. You know, I could set up some of them as inputs and some of them as outputs, but since they're all going to be outputs, I just clear that register. Then I need to enable my priority levels and high priority interrupts. So in the reset control register, or RCON, I need to set the I pin, which is interrupt priority enable bit. And then that enables my interrupts. And then in the interrupt control register, I have to enable my global interrupt. And so that's the GIEH bit. And then before I enable the timer interrupt, I want to go ahead and clear the interrupt flag just in case. That way, if I don't clear this and I enable it and the flag's already set, then I won't get to finish the rest of my initialized settings. And that could be disastrous. So first thing I want to do is clear the interrupt flag, which happens to be in the interrupt control register for timer 0 on my chip. If it was timer 1, the interrupt flag, I believe, is in the PIR1 register, and the interrupt enable bit is in the PIE1 register. So you really got to look at your data sheet and look at the addressing and the registers and the controls and all of that, because it can definitely be different from PIC to PIC. Next thing I want to do is move that initial value that we saw up here into the overflow counter. That way I have a start point. Okay, we're going to start here and we're going to make sure we're going to get through these cycles. So you've already seen those two commands. Now I'm going to enable timer 0. So far timer 0 is not on, but here I'm going to configure it and enable it. Now what I've done is I've configured it as an 8-bit timer, and then I've selected a prescale value of 1 of 256 or 255, however you want to look at it. And I've also set it to clock from the internal instruction cycle, not an external clock or a different clock method. And I've set it to clock on the rising edge, not the falling edge. And basically, you know, I've got 8 bits within that timer 0 control register, and the 8 bits that I've set or cleared end up equaling a hex number of C7. So I just put the hex number into the working register and then move that into the timer 0 control register. And once that's done, I'm going to set my first bit on port D, which is bit RD0. Now the reason I've done that is because if I don't set it, then when we start rotating to the left, all we're going to have is all zeros, so we'll never see an LED set. Now, you might be asking, well, why don't you just do that in the main program? Well, I did try that, and if you try it, you'll see why. Basically what will happen is if we put this in the main program, then RD0 is going to stay illuminated and we'll never see any change. It won't rotate to the left. And the reason that happens is because every time that this interrupt routine is returning, you know, when we return from the interrupt, it returns back to the main program. So when it does that, it says, oh, well, set RD1 high. So it never really gets to toggle, you know, to set RD0 low and RD1 high. It just stays lit. This will stay lit the whole time because everything's happening so fast, and every time we leave the interrupt routine, we come back, and so it never gets to rotate the bits, and that's not really what we want it to do. So if we just set it up here, it never comes back to the initialize label. You know, it'll never come back to that. So we set it once, and then it starts rotating, and then we determine whether we want to go right or left based on this code here. Every time we return from the instruction, we come to main, and you'll see the program will loop here continuously until an interrupt is received. Upon completion of the interrupt, the program returns here and waits for the next interrupt. And at the end of main, it just keeps going back to main. And so it'll just keep doing this until an interrupt is called. Come up here to the interrupt routine, and it just bounces back and forth. And so that is it. And hopefully you were able to, you know, pause here and there and copy the code and get it going. You know, I have no problem with you copying it. I hope this has helped. I know I had a lot of problems getting the timers and the interrupts working, and this seems to work. Like the lat A command, I don't know that I really need that. You know, I don't know that I need the lat B command. Really, I think all I need is to clear the port and clear the tri-state registers. But it works, so I didn't try changing it. So once you've got it all written out, and you're sure you've got your linker file added, you can do a clean and build on it. And when you do the clean and build, you just watch the dialog down here to see if you have any errors. And if it builds successfully, you're good to go. Now, sometimes, like let's say we had this definition skip in the second column, and we did a clean and build. You can watch this, and you'll see that link appear. Now it's still built successfully, and it should still work. However, we got this warning, hey, you know, we found this label after column 1, and if you click it, it'll take you right to it. And you say, oh, okay, well, put it in column 1 then. And then clean and build it again. And you can do this as many times as you want, it doesn't hurt a thing. And it builds successfully with no warnings or no errors. Now if you got some errors, you really need to go back and take a look at it. You know, maybe yours calls for just WDT and not WDTEN. You know, so you gotta watch all of that stuff. And once you've done that, you can flash it with your programmer. And for mine, I have a demo board, and for some reason when I use the external power, you can't program it, because when you plug in the PIC, it will short out the power supply. So you go to project properties and PIC18F, drop down to power. You can choose to power the target circuit from the PIC18F, and I think they're pretty good about knowing what your appropriate voltage levels are. Like mine, I think 3.6 is the maximum voltage, so I just choose 3.25, apply, and OK. At that point, plug your PIC in to your programmer, whichever one you have, and then you select this button, which you can do a drop down, make and program device for debugging, or programmer to go if you want to just program your PIC18F and then bring that to your circuit. I always choose the first one, and then it will load the code, it'll create the hex file and load it onto the PIC. So I hope this has helped. You know, please feel free to like or hate this video. You know, feel free to subscribe. As I progress, I'll be putting more videos about PIC programming. And if you have any questions, leave a comment or send an email. And now I'm going to go ahead and go to a video showing you what this program looks like. Okay, so now we'll go ahead and do the demonstration part of this video. This is my little lab bench, and here's my little demo board. As you can see, I just have it set up to 2 D batteries, and I'll just plug it in, and you'll see these LEDs start going back and forth. And there you go, just chasing each other back and forth. And if I probe RA6 over here, as we were talking about earlier, you can see, well, I don't know if you can see, but that is a period of 4 megahertz. Or frequency, I should say. Not really the period. Anyway, back down to the board here. As a little bonus, if you watch my next video, I will teach you how to make it do this. So whenever it receives an interrupt from the switch, it just flashes them all on and off. And I've got that code written, but I don't like it. It's kind of ugly and laborious, and I want to refine it and make it a little better. But once I do that and get it operating in a different manner, then I will upload that video, and you should be able to just modify this code just a little bit to add that interrupt into it. So thank you very much.